Okay, so here we have virtual lecture number 3 on boring and carboring chemistry. Today, well, this time, we'll actually look at some carborings as well. So, before we do that, let's look at some chemistry of borings. And we'll do this with the same things that we looked at for the chemistry of diboring. Now, if you recall from class on Friday, the 15th, and also Monday, that's as I'm recording this today, the 18th, there's a difference in reactivity when you combine two ammonias with diborane versus an amine, where these R's can be any combination of hydrogen in an organic group, which excluding 3 hydrogens. So if there's one organic group or more here, you get one type of reactivity. With this, the same thing, but a different reactivity occurs with the ammonia. Now, it turns out that this also applies to the borane clusters. Now, so if you watch what happens here, we have this borane, B4H10, from our formula here. Right? We should be able to ascertain that that's an arachno cluster. And if we add to that ammonia, the exact same thing that we saw for diborane will happen with this. If we add ammonia to diborane, what happens in effect is that you abstract a BH2 plus ion. And the same thing is going to happen here. And to this, we're going to get coordinated two ammonias. So you've abstracted, again, a BH2 plus fragment from now our borane cluster. And again, this is the exact same thing that would happen if this was B2H6. All right, and then what's left over is the remaining part of the cluster here. And so, if you'd like, what we can do is the following thing. We can write this product salt that you get out like this. Okay, so these things, two things are the same. So when you do a problem like this, you can just go ahead and put the answer in this format. It's not very easy to predict, is this, what the structure of this thing here that we're going to get is, but that is actually what happens in this particular reaction. Now, the question that might be asked, though, is what is the structure class of this thing? Is it closo? Most certainly not. Is it nido? Which is possible. Or is it arachno? And And the answer is actually it's arachidone, because if you go back to the last lecture where we were talking about the formula types, right, the general arachidone formula is BNHN plus 6, but you could also have BNHN plus 5 minus, and if you note that formula of that product, anion fits exactly with what we said. You also could figure that out from the Wade-Mingos rules. And so we won't go through that, but you should try that to make sure that that's actually the answer that you get for this particular part on your own. So any cluster here, when reacted with ammonia, will result in abstraction of a BH2 plus cation, and the formula of the thing that you get left is whatever is subtracted from that, BH2, with a negative 1 charge. So that I could have made this just anything. Now there's one thing to note about this, and that is that this reaction that I just showed you, oops, happens only for 2 of the 3 structural types. And those are, as you saw from the last reaction, arachidone and also nido. You actually have to have a bridging hydrogen present for that reaction to proceed. Okay, so the reaction with ammonia will happen only with arachidone and nido clusters, and what you'll do is you'll abstract a BH2 group. So that's one type of chemistry, one type of reaction that occurs. Finally, then, as a side note, note that B2H6 is a nido cluster, and so that's what happens with it as well. Deprotonation is also possible. Again, this applies only, though, to our 2 open structural types. Deprotonation assumes that you're taking a proton off of the cluster, and indeed you are. But only hydrogen atoms involved in a BHB 3-center 2-electron bonding situation will do this. So the terminal BH groups that have 2-center 2-electron bonds are inert. So they don't react with the ammonia either. So a Closel cluster doesn't do the previous reaction. You don't abstract a BH2 group from there. So how are we going to affect this transformation? Like so. We'll start with a nido cluster. If you add to that any amine where all 3 R's are not hydrogen, one of them can be, or 2 of them can be, but not all 3. So a primary, a secondary, a tertiary amine will do this. What you get again is a salt. You generate an ammonium cation. So what this amine is doing is it's pulling off one of the bridging hydrogens giving you the ammonium cation and collapsing the structure a little bit down to give you this anion. But if you check out the formula from last time, or apply the Wade-Mingos rules, you'll find that that cluster anion is nido. So the punchline here on this is that if you start with nido, you end up with nido. If you start with arachno, you end up with arachno. Okay, so that does not change. So what exactly is going on here? If you look at the actual deprotonation, we have somewhere in our nido cluster, one or more, usually more, BHB bonds. And these are a 3-center 2-electron. Along comes the amine to remove the proton. And what happens is the 2 electrons that were holding together this fragment are still there, right? Because you're abstracting H+, a proton. How many electrons does a proton have associated with it? 0. So there were 2 electrons in this 3-center 2-electron interaction. You abstract the proton, but the 2 electrons that were there are still there, and so you form a boron-boron bond that is 2-center 2-electron. And then the underlying proton right there is the one that was right here. So if you consider then what's going on with that, why does the structure not change? Well, remember, it's the number of vertices, the number of boron atoms, and the total electron count that determines the structure. So in this reaction right here, the electron count doesn't change. So we have the same number of boron atoms, we have the same electron count, because what you removed is this proton that has no electrons with it at all. So because the number of boron atoms stays the same, the number of electrons stays the same, the geometry stays the same. The only thing that you're doing is generating now a bona fide 2-center 2-electron bond between 2 borons, which can also happen. So the last thing to note about this is what's the trend in acidity? Well, I'll give you an example of 3 different clusters. We got 2 nidos and 1 arachno. Now you may think, well, maybe it's the structure type that influences this. It actually isn't the determining factor. So here's the ranking for these 3 clusters shown right here. And we could have had a larger arachno cluster as well. We could have all arachno clusters, whatever. The actual determining factor for acid strength in these things, now remember, the closo ones are not acidic, so that's something we should note specifically. Those protons are all terminal in there. They are not acidic. It's only the bridging ones that are. So what determines acid strength? It's the cluster size that determines the acid strength. So you can compare arachno to nido. It doesn't really matter. The larger the cluster is, the more acidic it is. And so this one here with 10 borons in it is more acidic than this one with 5, which is in turn more acidic than this one with 4, despite the fact that they have different geometries. So for our purposes, let's ignore the geometry and rely on this statement right here that acid strength increases as the cluster size goes up. So that's somewhat of interest. Why is that? Well, it all has to do, of course, with thermodynamics, right? If a reaction is going to happen, it's going to happen based on delta G, more specifically on delta H. If it's thermodynamically downhill, it goes. If it's thermodynamically uphill, it does not go. But what influences? Stability of things generated influences that. So let's consider two things. Hexanol and cyclohexanone. They're essentially isomers of one another. Do you find either of those to be highly acidic? And the answer to that is no, you don't. Their pKa's are pretty high, and so they don't behave as an acid. But if we take one step further and consider this thing, which is commonly known as phenol. Is that acidic? Yes, it is. If you get these two things on your skin, you can wash them off, no problem. This will actually cause burns on the order of acetic acid or sometimes even dilute hydrochloric acid. So why is this phenol acidic while this cyclohexanol, let's say, is not? The answer has to do with the stabilization of the conjugate base, right? So if I were to deprotonate cyclohexanol, what I would get would be this. There's a negative charge here. When I deprotonate phenol, I get a negative charge there as well. The difference is that the negative charge on the phenol can be delocalized into the aromatic ring. Consequently, phenol's conjugate base is really stable due to that delocalization relative to hexanol, cyclohexanol that is. And this parlays directly into why the borane cluster's acidity increases with cluster size. larger the cluster is, the more delocalization there is in the cluster. So the bigger the thing gets, the bigger the molecular orbitals are, and so the more delocalization there is that occurs. This stabilizes the deprotonated cluster. So the larger the cluster is, the more delocalization you get. When you remove the proton, the more stabilized, the more delocalized is the negative charge that you generate from that. So the bigger it is, the more acidic it is. And so this is an example of organic chemistry applied to inorganic chemistry. All right. So finally then, in this context, the last thing we'll look at, that's the only chemistry we'll talk about at this point, are carborines. And so what these have is a carbon replacing a boron-hydrogen vertex. They fall into the class of heteroboranes, because it's not just carbon that does this. You can replace the borons with group 15 elements, you can replace it with other things, and so it's actually a diverse group of materials. We'll look at the carbon substituted ones as it is. And so what you do is exchange, in quotes. Again, this is a thought experiment. What you're doing is you're exchanging one or more BH minus fragments. With carbon-hydrogen fragments. These two things are isoelectronic, which means they have the same number of valence electrons. There's also something more significantly important about them, and that is that they are also isolobal. They have those electrons disposed in the same types of orbitals. And because of that, you can, chemically, in fact, substitute one of these for one of these, exchange a BH minus with a CH free. And that's how these things are actually prepared. So for the synthesis, here's how it goes. These are typically constructed from a nido borane, and that's what we have here. What happens with this nido borane is if you combine that with diethyl sulfide and some heat, and hopefully you've got some breathing apparatus on, because not only does this smell really bad, like rotten eggs, it's also toxic, so you've got to be careful doing reactions like this. What that will do is substitute out, so we need 2 here, 2 of the hydrogens on the borane. And you can guess which hydrogens those are. Those are, again, the bridging ones. So that's why we start with a nido cluster. The closed-hole clusters are pretty much entered. And so that's the impetus for using this type of starting material for it. And so this comes from bridging hydrogens. And so it turns out when that happens, though, the electron count is unchanged. And so this is still, formally speaking, a nido cluster. But again, we don't have to worry so much about that. When you then take that material and combine it with acetylene. And again, this involves some heat. I didn't put the arrow there yet. There we go. That will drive off the diethyl sulfide and give us a cluster with the formula B10, C2, H12, and dihydrogen. Okay, so this is lost. The carbons actually get placed into the cluster themselves. And so effectively, and again, note this is a nido material still. If it weren't, this next step probably wouldn't happen either. Okay? Pi electrons in acetylene replace the 2 pairs of electrons donated by the thioether groups. So what actually happens then is now going from here to here, there is a change in the electron counts. As Hans and Franz say, you can hear me now, believe me later. If you look at this formula, now it isn't so obvious what the geometry is, right? Because you don't have borons and hydrogens only, you've got carbons. So just for the sake of the exercise, let's determine what geometry we have using the Wade-Mingos rules. And so 4n plus x is equal to the number of valence electrons. If you're paying attention to what I just said about the electron change, you probably already know. But anyway, let's do it just for the sake of practice, because this will be, again, something you'll be faced with on the homework and exam situations. What's the number of vertices? Well, before, it was just the number of borons. In fact, now, it's also includes the number of carbons. And so, for our species here, the number of vertices is 12. In fact, for any heteroboron, so if I did something crazy like put an arsenic in there or something like that, which you could do, the number of vertices is always the number of borons and the number of heteroatoms. An arsenic, a nitrogen, a phosphorus, in this case a carbon. You could do this with silicon. You could do this with germanium, anything like that. All right, but the important thing is to be able to count up the number of vertices. So we've got that covered. What's the number of valence electrons in here? We have 10 times 3 from the borons. 2 times 4 from the carbons. And 12 times 1 from the hydrogens. Note, there is no charge, so you don't have to add 1 or 2 extra electrons to get the total. So, with that being said, what do we got here? A 30, an 8, a 12. So our total number of valence electrons is 50. That number should look familiar. If we then plug in our number of vertices, what you're going to get is 48 plus x equals 50. X equals 2. You've turned a nido cluster now into a closo cluster. So this is where the Wade-Mingos rules come in handy, is when you have heteroboranes and you don't know just by inspection what you have. And so you'll see exercises with carboranes where you've got to figure out their geometry. And so, on your handout here, on the very last page, you actually have a picture right up there in the top left of the carborane we just made on the board. And so the product of this reaction is closo 1,2 B10 C2H12. So the 1,2 for this tells you that the 2 carbons are right next to one another. And we won't get into how the nomenclature of these things either. That's just mostly for your information. That's what you get initially out of the reaction. The 2 carbons are still bonded together as they were in the incoming acetylene molecule. So, though, what about this stuff? It's air stable. Any of the borane clusters that we had up here, which I didn't mention at the time, but anything with just boron and hydrogen is not. Those will react quite excitingly with oxygen or moisture. So these are actually air stable. If you heat this to 500 degrees, it isomerizes. And so what you get then is the 1,7 version, and so that's actually shown on your sheet right here in the bottom left. And if you heat that further, or just directly, and I summarize this again, 2 was actually the thermodynamically most stable version, or isomer, if you will, and that is the 112 isomer, and that's the one that's shown right here in the top. So if you look at these structures, by the way, before we jump ahead, right, the carbons here and here, or here and here, or here and here, have hydrogens attached to them. And so there is some chemistry one can do with these molecules as well. And so those carbon-bound hydrogens are slightly acidic. Okay? Not HCl, hydrochloric acid acidic or anything like that, but you can abstract them. And so of any of the 3 isomers that we have there, you can take that and hit it with 2 equivalents of N-butyl lithium. So N-butyl lithium is a pretty strong base. So maybe slightly is a bit of a weak term for how non-acidic these things are. But this isn't bad stuff. It's easy to handle. You can do this. And what you'll do is generate two molecules of butane as the non-interesting product, and this dilithio cluster shown here. So what happens when we do this is that 2 of the hydrogens come off, and those are the 2 that are attached to the 2 carbons that are present. Now what you've got is a nucleophilic cluster. And you can take that and add to it. So I'm going to rewrite it with the cation first, as should be. Write that with a halogen. And that can be any halogen, in this case iodine. Treat it with carbon dioxide, and that's got to be 2 of those. You'll generate a borane cluster carboxylic acid. And there's a whole bunch of other things that one could do with this. And so these things, these carboranes, are actually used to build a whole bunch of different structures. And when we get to it much later in the class, towards the end, and we start talking about organometallics like ferrocene, these can be used in place of a cyclopentadienyl ring to build transition metal complexes and stuff like that. So anyway, there's a lot of chemistry that one can do with this. And so, again, are all carboranes closo? Of course not. So let's just wrap this up. With a little more practice using the Wade-Mingos rules. So give you that. What's the structure of this? What's the total number of electrons? 3 times 7 for 3 borons. 2 times 4 for the carbons. 13 times 1 for the hydrogens. Our total is 42 valence electrons. The number of vertices is the number of boron atoms, 3, number of carbon atoms, 2, and that gives us a grand total of 5. So, X is some very large number. This formula is actually an invalid formula for a cluster. Because I wrote it wrong. That should have been a 7. Okay. So, again, let's take that formula. This is the correct electron count. 7 times 3, 2 times 4, 13 times 1, 42. The number of vertices is not that, but 9. 4 times 9 plus x, that's 36, and so x is 6. And that's arachno. How about something a little trickier? I give you that formula. All right. So one of the things you should be able to do is realize that this is a cluster anion. With a -1 charge. The reason that you know that this has a +1 charge. So now, nine times 3 for our borons, 2 times 4 for our carbons, (12 times 1 for the hydrogens, and a -1 charge means we add 1 more electron. We have 11 vertices. And so using the Waite-Mingos rules, X is 4. We have a nido cluster. And so carboranes, like boranes, can be nido or arachno. And so those are essentially all of the things that you need to be able to do, I think, to complete homework number 2. And so determining a parent structure from a derivative structure, we've got that. Determining the structure period, counting electrons, acidity, all this kind of stuff. All of this should be in these 3 lectures that we have here. So again, if you're having any trouble understanding any of this, send me an email, or we can Skype about it also, if that would be easier for you to understand. So the next virtual lecture will not be covering anything on the homework assignment, but it'll be something that we'll talk about when I return next week, and that is actually the chemistry of aluminum.